Ever wondered the probability that someone else is the imposter? Ever wanted to know the optimal strategy to win a game as a crewmate? Well, this is the place for you. Here, we'll be discussing probability in Among Us. To start, we'll be looking at a simple probability. To do this, we make some assumptions to allow the calculations to be easier and simpler to understand. We assume there are 10 people playing and that your colour is always the same. Let's say blue. This is to make things less confusing when we're talking about other players. Also, assume that purple is always playing. Finally, assume the chance of anyone being the imposter is completely random. Let's not forget about this since it's really important. Now let's begin. We'll be skipping some of the simpler ones as they should be easy for you to compute, but they will flash on the screen now for your benefit. Let's say there are 2 imposters and you are a crewmate. You feel like purple is a bit suspicious. Could they be the imposter? Well, this probability is straightforward. Since there are 2 imposters and 9 other people besides yourself, the probability is 2 over 9. This can be done with the probability tree, which we'll talk about much more later.
Now let's consider certain scenarios. For example, let's say that 4 people are dead because an imposter killed them. For the purpose of this, we assume that both you and Purple are still alive, and you're a crewmate, as it wouldn't help much being an imposter. For 1 and 2 imposters, what's the probability that Purple is an imposter? Starting with 1 imposter, we can begin to lay the foundations for calculation. Since all 4 people were killed by an imposter, then we know they were all crewmates. So, we need to consider the remaining 5 people. Since there's 1 imposter, then the probability is 1 in 5. Easy. And if there are 2 imposters, then it would be 2 in 5. Now assume that they were all randomly ejected instead of being killed. Emphasis on random, as this is very important. Using the same assumptions, as well as assuming that the game doesn't tell you what role the person was when ejected, we can consider this with 1 and 2 imposters. With 1 imposter, it's fairly boring. Since the game hasn't ended, we know that 4 people who were thrown out were all crewmates. So the probability is the same as before, 1 in 5. Considering 2 imposters, it gets really interesting. Since the game doesn't end with 1 imposter being thrown out, then there could be 1 or 2 imposters left. This means we should formulate a probability tree to understand what is going on and to calculate each individual probability.
This tree will have 2 branches after every decision and has 4 rounds of branches, 1 for each ejection from the ship. To start, we have 2 branches like we said, 1 for a crewmate to be ejected with probability 7 over 9 and 1 for an imposter to be ejected with probability 2 over 9. We won't do every single probability, but we will consider the scenario of the imposter being ejected after the first round of voting. Again, there are 2 branches, 1 for a crewmate being ejected and 1 for an imposter being ejected. The probabilities for this will be 7 over 8 and 1 over 8 respectively, as there is 1 less person who was an imposter. If the other imposter gets ejected, then the game ends, so no more branches from that. We can calculate the probability of this by going back up the branches and multiplying the probabilities together. For this, it will be 1 over 8 times 2 over 9, which gives us 1 over 36. Now with this information, we can complete the whole tree knowing that the game ends when 2 imposters are thrown out. Here we could see there are 3 different situations, 0, 1 or 2 imposters left. In this tree, the game ends with 0 imposters left 6 times, each with probability 1 over 36. 1 imposter occurs 4 times, each with probability 5 over 36, so in total 20 over 36 or 5 over 9. And finally, 2 imposters happen only once with probability 5 over 18. But we have assumed that the game is still going, so it is only possible that we have 1 or 2 imposters. In fact, the probability of 1 imposter when the game is still going is 5 over 9 all over 5 over 9 plus 5 over 18, giving us 2/3. And the probability of 2 imposters is 5 over 18 all over 5 over 9 plus 5 over 18, giving us 1/3. Looking at these Venn diagrams, it is clear to see why this is the case. There could be 1 imposter left out of the other 5 people, so 1 over 5 times the probability that there is 1 imposter. This is 1 over 5 times 2 over 3, which gives us 2 over 15. When there are 2 imposters left, there are 5 other people left. So the probability is 2 over 5 times 1 over 3 or 2 over 15. So we need to sum these 2 probabilities together to get 2 over 15 plus 2 over 15, which equals 4 over 15.
But it doesn't take into consideration whether someone was far away from the body, or they were with someone, or have some sort of other alibi. The only way to use these considerations is to do some research, which means playing a lot of games and recording the data from them. As a group, we have recorded over 100 meetings, so this is considered a large data set, resulting in a more reliable answer. The first thing to note about the data is there is a large variation between public and private matches. This drastic change in probability is due to people knowing each other better in a private match, but not in a public match. This is first obvious when you consider the success rate of voting out an imposter. In a public game, when not skipped, is about 51% successful, whereas in a private, it becomes 72% successful. In addition, a meeting ending in a skip vote for a public and private match is 25% and 36% respectively. Combining this information, we have that a public game, the chance of voting off an imposter is 38%, two significant figures, which is 1 minus 0.25 times by 0.51. For private, this is 46%, or 1 minus 0.36 times by 0.72.
The data collected can be used to show the rate of kills per round. We find this by using the mean as there are no extreme outliers. We found that private and public games were very similar, with public games having 1.6 kills per round and private games having 1.5 kills per round. When 10 people are alive at the beginning, the mean deaths is 1.4. This is quite a low probability, because everyone is in the starting room probably doing their nearest tasks first, and when an imposter kills, they can be detected rather easily due to everyone being in the proximity. It then jumps up to 1.6 for 8 to 9 people alive, as it's likely that people have spread out to do the tasks and won't be keeping an eye on each other, allowing the imposter to strike. It then drops to 1.25 deaths per round for 6 to 7 alive. At this point, people will be starting to whittle down the suspects to the imposter, and this will limit on where or who they can kill. For the remaining people alive, the average kill is 1, as there is likely only one imposter left, and crewmates will be starting to finish tasks, so will be either looking on cams or will actively be searching for bodies. This information can be useful to work out whether to skip if there are 6 people left and 2 imposters. If you skip, there is a 25% chance the imposters will kill 2 people and win. However, there is a 75% chance you'll find the first body before a second kill is made, meaning you get to the next round with less people to choose from and more information, increasing the chance of you voting correctly. Which suggests it's better to skip, as you have only a 72% chance in private and 51% chance in public games to get the imposter in the vote. And if you are wrong due to the rate of which people get killed with only 5 people left, it is very likely one person will die and the imposters will win.
What have we learned? Well, probabilities can be made easier taking specific assumptions and then building up from that. Probability trees are a key tool to lay out your findings, and it allows you to approach the question statistically. But most importantly, trust the numbers and don't let suspicions get in the way. Thanks for watching, and don't be sus.